Hello everyone. Thanks for joining us here today for Bruker's webinar on improving yields, 3D static and dynamic MEMS characterization. Just a couple points before we begin. Everyone will be muted for the duration . All right, is this working? Can you hear me now, Sarah? Hello? Hello?
Yep. Hi, Eric. Yep, we can hear you again. Thank you.
All right, good.
We lost you at the very beginning of logistics.
All right, everyone, sorry. Yeah, we'll start over here, folks. My apologies. So just some brief logistics before we begin. Everyone will be muted for the duration of the webinar. We ask that questions be typed into your chat window, and we're going to get to them at the end of the presentation. Also, after the webinar, we have a brief 5-question survey that we'd appreciate you answer before logging off so that we can improve our future offerings. And last, we will provide a full recording of the webinar online and send a link within about a week from now. And so you will have access to this should you wish to share it with friends or colleagues. So just a brief introduction of myself. My name is Eric Novak. I'm the Director of Technology Development here at Bruker Nanosurfaces, Tucson. My contact info here. If you have questions after the webinar, I'd love to hear from you. A little bit of personal background. I got my PhD from the University of Arizona Optical Sciences Center in 1998. I actually started as a student with then Wyco, which later became Vico Metrology and is now Bruker Nanosurfaces. And so I've been here about 20 years now and involved kind of in all aspects of precision metrology system development and verification. Just a brief one-slide introduction to the division if you're not familiar with what we do. Bruker's Nanosurfaces division essentially concentrates on precision scientific and industrial instrumentation in 4 main areas. We have a scanning probe microscopy, AFM group, that has a variety of offerings from, very value priced, high capability offerings all the way to full semiconductor automation solutions running 24/7 in fabs. I'm here in Tucson, Arizona, and we primarily focus on 2 product lines. One are 3D microscopes, and the other is stylus profilers. And then we also have another division in California that produces tribological and mechanical test equipment. So they look at corrosion and wear studies and can automate those and characterize what's going on almost any surface, from orthopedic implants down to MEMS devices or petroleum components, things like that. A little bit of introduction to the topic today, probably familiar to a lot of you, but why the focus on MEMS, why this webinar? Well, the MEMS market is large and continues to grow at a very rapid pace. So the MEMS equipment market even is expected to hit $500 million in 2012. You can tell that MEMS production is gaining traction because even Applied Materials now has entered the market with a DRIE tool for enhanced MEMS production. And what this ultimately means is there's more players entering the marketplace, there's more competition, and that's creating greater demands on product development velocity as well as quality. And just where are MEMS, for those of you not familiar with the entire field? One of the interesting statistics I've read, some reports say that an average American or an average consumer will encounter more than 100 MEMS devices today or each day, but at the very least people are encountering dozens of MEMS devices. Everything from the components in the cell phone that can determine its orientation to the airbag sensors, tire pressure sensors, and environmental controls within your automobile. And so increasingly MEMS are replacing traditional larger devices and providing superior quality and superior reliability for a lot of different businesses. But it's still a barrier to have MEMS devices adopted in certain areas. So most industries actually have traditional techniques that are known reliable solutions. So radio circuitry, mechanical gyroscopes, analog sensors are all well tried and true tested devices. And even though MEMS offer significant, sometimes cost savings, significant performance enhancements, they really have to prove their worth in almost every category. So cost, size and weight, performance characteristics, and reliability. And surveys consistently show that reliability concerns are a primary barrier to adoption of MEMS devices. And packaging and test of MEMS devices remain critical parts of the process. Even after more than, I'd say, 15 years of widespread commercial adoption of MEMS devices, packaging and test still remain about 60% of the total cost of a lot of devices. And that's significantly higher than a standard semiconductor product or a standard component that you'd put in, for instance, the traditional larger components. And just as further validation, a MEPTEC report that came out last year highlighted a few areas where, metrology of MEMS devices remains important, remains a barrier. So with MEMS development, there's large numbers of process iterations. Those can take weeks or months. Surface conditions are usually affected by the processing steps. And the device's 3D geometry actually has a significant effect on development problems with the MEMS devices, particularly contamination. And all of those really create a high demand for metrology in MEMS. And just to look at some of the MEMS failure modes, this is a bit of an eye chart, but you can see that each of the different primary MEMS devices have significant numbers of different failure modes that need to be tested and verified to ensure proper device performance. So you have everything from contamination to environmental creep, leakages, strange deformations that can happen, outgassing that can affect performance, effects of temperature and electrical shorts. So comprehensive metrology does play a key role over the entire MEMS production cycle. So during R&D, you want to measure the real device behavior without effects from packaging typically. During pre-production, rapid, accurate metrology can shorten your feedback loops and make sure your devices are rapidly iterating towards a final design. And then during production, MEMS actually undergo a very high test rate to maintain adequate process control, to provide further cost reduction as you're feeding problems back into the production cycle, and then also for failure analysis to ensure that any ongoing problems are rapidly caught and the root cause failure discovered. And then in post-production, there's a lot of longevity and cycle testing of MEMS. There's lots of tests that go on relative to endurance and environmental analysis. And then MEMS are always being enhanced. And just the picture on the right comes from TI, and it's a representative cartoon of the micromirror arrays used in most projectors. And you can see just the complexity of the devices. There's literally 10 layers and probably 15 critical components per mirror, all of which that need to interact properly for proper device performance. So people will characterize feature heights, lateral dimensions, line widths, angles, radii of curvature. They'll look at stress. Roughness is very critical, both in MEMS that are doing optical things such as the micromirror arrays. In biological samples, it can affect adherence and acceptance by the body, and it can also lead to defects and other problems. And then defects and contamination need to be characterized as well to ensure that the devices are going to perform properly. And then different MEMS metrology techniques really have different strengths, and there's not one technique that can do absolutely everything. So I thought this chart was useful because it kind of highlights the four main areas that are used for MEMS test. So the first are 3D microscopes or optical interferometers. The second category are stylus profilers, which are really the workhorses of any metrology lab. It's usually the first characterization any metrology lab gets, and the one that's kind of most readily used by a wide variety of people. Atomic force microscopes and scanning electron microscopes. So in terms of quantification, the SEM probably provides the least quantification, but I'd say you're going to see the most SEM pictures in literature because it provides a very nice picture that kind of people intuitively understand. Optical interferometry, 3D microscopes provide non-contact, non-destructive methods. Stylus, they'll contact, but you can get very low force so as not to damage the devices. AFM is really, you can argue whether it's really contact or not, but it's a non-destructive technique. SEMs are often non-contact, but there can be problems due to charging, and then sometimes you have to cross-section. And so it can be a destructive test. In terms of acquisition speed, 3D microscopes are going to be the fastest. SEMs and AFMs are going to be the slowest, typically. And in terms of time to result, an SEM typically requires the most time to result because of vacuum, cross-sectioning, and general system usage. Vertical measurement range, there's a wide variety here, anything from up to 10 millimeters on the optical side down to 20 microns on the atomic force microscope side. Vertical resolution, almost all of these will have acceptable vertical resolution on the order of an angstrom or a few nanometers. So that's generally not a concern. Lateral resolution, most MEMS devices are in the micron to few micron size range all the way up to millimeters. And so most of these techniques are acceptable. There are some devices where stylus techniques may not be ideal, but any of these techniques generally provide the lateral resolution. If you need to look at sidewalls or undercut, you're going to need an AFM or an SEM to do that. And if you want to look at packaged devices, so if you want to look at something for which there is no physical access, your only choice essentially are the optical techniques. And last, the only technique that really is capable of doing dynamic measurements is a 3D microscope. And we'll get into how that's accomplished later. In terms of price point, there's almost a price that suits any needs. Most of these technologies are fairly mature, and so you get a fairly broad range of pricing depending on your need. So the remainder of the talk is going to really concentrate on 3D microscopes, because we've seen over the years that of the various technologies we're aware of and that we offer, in the MEMS field in particular, 3D microscopes are really the most widely adopted measurement solution. And they're very simple devices in principle. They're just modified bright field microscopes where you add a precision scanner and a specialized objective. And when you do those two things, you're able to get a signal back that allows you to do three-dimensional capability. And really, in terms of the specialized objective, what we're doing is we put a beam splitter in the objective, which is the bottom blue bar you see. And that splits the light, and part of it goes to your sample, part of it goes to a very small reference mirror that's of high quality. Light bounces off both the sample and the reference mirror and gets recombined. And we can look at that recombined light and essentially compare the sample to our reference and get three-dimensional height. So it's a fairly simple technique, a very powerful technique. What does that look like in practice? This is about a 3x slowed down measurement where you scan the microscope objective through focus, and you see those bright and dark bands. On the right here, we actually are looking at a step height. And when those bands go by, we track the position of those bands versus the height of the objective that was scanning through focus, and that allows us to get a three-dimensional map. So one of the advantages of interferometry for MEMS devices is there's no loss in vertical resolution no matter what your field of view is. Again, this is a microscope. And so I can pick an objective that's a 1x objective with a 15 millimeter field of view, or I can pick a 115x objective with a 10 micron field of view, and almost anything in between. And as you scale your lateral resolution and your lateral field of view, you get no loss in the sub-nanometer vertical capabilities. And so even on a device like this microgear, you can see print through from the manufacturing process, from the lithographic process. Very fine details can be imaged even over large fields of view. It's a mature technology, and so 3D microscopes actually offer very advanced feature finding software. So they can take an image, they can segment it, and report statistics on each segment of the image. So in this particular case where we're looking at a micromirror array, we can look at tilt, roughness, curvature. We can look at relative heights between the regions, and you can actually look up to thousands of regions within a single measurement and characterize those. And you can also report steps, angles, and roughness for each region independent of the others and then aggregated together as well. A lot of MEMS, particularly in development, quantifying the stress of the processing is extremely important to get good device characteristics and really to dial in the process. You can very rapidly measure a cantilever array, look at the curvatures across each of the cantilevers, and determine the stress that's been induced by the etch or deposition processes that the devices are undergoing. You can also characterize complex geometries like microfluidics. You can look at etch characteristics. These devices can do volume calculations, look at uniformity, particularly in things like microfluidics. The roughness of the channel, the volume of the channel are very important in terms of how fluid flows through them and the end device characteristics. The other thing about, again, we mentioned an optical technique, is you can actually measure the microfluidic channels through the encapsulation material so that you can actually characterize the volume of the channel rather than just looking at the bottom surface. 3D microscopes can also be used to quantify film thickness, and that can be anything from quantifying photoresist, which is really important, particularly in etch processes. If you need to know the etch rate, you can pull parts out, characterize the photoresist thickness, very precisely dial in the etch rate. You can look at the thickness of polysilicon. Inherently, it becomes opaque only really as you go into the blue and green regimes, and so 3D microscopes can look and characterize polysilicon thickness. And you can also look at protective coatings that are used to reduce friction or wear or other properties. So essentially what happens in a microscope is every interface creates a reflection. So you get a reflection from the air-film interface, and you get a reflection from the film substrate interface. And as long as those interfaces are separated by about 1.5 microns, it can be a little lower for some materials, all the way up to 600 microns, we can analyze those two signals separately and do characterization of the top surface roughness, top surface shape, bottom surface characterization, as well as look at overall film thickness. And then there's also specialized objectives that are available, again, to support measurement through very thick materials. For instance, into environmental chambers or through thick encapsulation. So on the upper left, we see, what would the signal, and again, these bright and dark bands you kind of see washed out on the upper left and more firmly on the upper right. Those are really the signal that's being used to do the characterization. So with specialized objectives, you can go from very weak signal looking through encapsulation to have a very strong signal that, again, can give you very precise characterization of mirror arrays. In this case, this mirror is courtesy of Sandia National Labs. Also, very recently, there's been advanced techniques introduced in 3D optical microscopes that significantly enhance their lateral resolution. So just a few years back, people would say the lateral resolution limit of a typical optical microscope resides somewhere around a half of a micron, 500 nanometers. But with new techniques that involve modeling and multiple measurements, we have a patented technique called Acuity XR. You can actually significantly enhance the lateral resolution of your measurements. So here I've zoomed in on a 10x measurement of the edge of a microgear. And on the left, you can see there's some pixelation, some loss of resolution. And on the right, it's the same exact part using the same exact objective and camera, and we get a significant enhancement in the lateral capabilities of the instrument. What that translates to is we've actually seen more than a 3x gain in gauge capability on things like widths, heights, areas, and volumes using this technique. And it actually allows us to image structures all the way down to 130 nanometers wide. And that's more than a 3x improvement over anything that used to be specified in the literature. But really, one of the unique characteristics of MEMS devices is that static measurements are not enough. So it's great for quantifying the surface. It's good for figuring out if there's defects or if there's gross problems, but it doesn't really tell you how a MEMS device is going to perform in practice. For that, you really need to measure the device dynamically. And dynamic measurements, they quantify the true device functionality. And micro-device operating failure modes differ significantly from the non-operating failure modes. And by that, we mean, what's going on in terms of wear, in terms of asymmetry of motion, and other things. So if you look at the video on the lower right, again, this is a resonator that came to us from Sandia. If you just look at the center circle, we would like this device, it's being driven by a symmetric voltage signal, so we'd expect symmetric motion around the center. You can see it moves way more to the left than it does to the right. And that means that depending on how this device is oriented, it's actually going to perform differently as a sensor in one orientation versus the other. For instance, if this were an airbag sensor trying to look at deceleration, one way versus the other, you're going to get a stronger signal. And so you need to really characterize the moving structure. So you look at shapes, distortions during motion, radius of curvature, sag, bow deflection. What is the range of motion? What is the rise time? What is the settling time? And then you can also characterize the resonant frequencies of the devices very precisely using dynamic techniques. So you need to be able to do both in and out of plane motion. You need to be able to look at both static and dynamic. So how do we actually do dynamic measurements using a microscope? Well, the technique is fairly simple in principle, a little more complex in practice, but it's via strobing. So if you look at the diagram on the bottom, our camera, in terms of the MEMS devices, which are typically, they'll have resonance frequencies in the kilohertz range, maybe even in the megahertz range. But the camera typically is, they're integrating a 30th of a second, things like that. So it looks at light over a very long period of time. The MEMS device over that camera frame is going to move a lot of cycles. But if I have my light source that is precisely synchronized with the MEMS motion and I strobe it, it essentially freezes the motion with respect to the camera. The camera only sees the device, in this instance, at the bottom of its cycle. And if I then move that strobe to a different relative phase with respect to the MEMS device, I see the motion at a different point. And so I can build up a dynamic picture of what the device is doing. And I can look at different frequencies, different voltages, different drive signals. And all of that looks frozen with respect to the camera, so I get the same high quality results, but I can actually measure things up to 2 megahertz frequencies. One thing I did want to just briefly mention is that MEMS devices often require additional hardware that should be considered when you're looking at metrology. What is the capability in terms of being able to handle the additional hardware, and is it sufficient? So it's easiest to test devices using ZIF sockets, so that's usually an important thing. The actual mounting of MEMS devices is extremely important for good characterization. So they're small devices, they are fragile devices. One of my favorite experiences was when one of our product managers accidentally sneezed onto a micromirror array, creating essentially micromirror confetti in the lab. But so you need to be able to fixture these, you need to be able to protect them. A lot of times you're going to want a vacuum fixture, but because MEMS have so many different characteristics, so many different sizes, you want something flexible like a porous ceramic chuck so that you kind of put any size device on there, hold it very securely and safely, and do nanometer level metrology. And then also being able to handle probe platters so that you can use magnetic probes or vacuum probes, but in order to actuate the device you need to provide drive signal to it. And so making sure you have the real estate to do all of that is important. And for instance, we have a line of 33 millimeter working distance objectives that were primarily designed just to give people that additional access so that their part can be well removed from the metrology head. And as you do dynamic measurements, you can actually see and measure coupled 3D motion. So in this particular case, on the left, I have a measurement where I've subtracted two results. So I've looked at the MEMS device at two different points in time, and I've subtracted them, and it's a false color where red is high and blue is low. And you can see the device in the 3D image on the right, it's tilted. It's been twisted as it's actuated, and so something's going on. And so in the center, we can actually break the device into a whole bunch of different subcomponents, characterize each of those subcomponents, and really very accurately get down to what is going on in terms of tilts and translations of each subcomponent and see if we can find the problem area. And then I've already shown you guys some of the 3D animation, but being able to take your measurement sequences and put them together into an overall movie is often very instructive. So here we have a micro gear array rotating, and a lot of times it's very instructive to see is it translating back and forth as it's spinning? Is it moving in and out of plane? There's a lot that can be gained just from visual analysis, let alone the mathematical quantification. And then there's sometimes that dynamics are needed just to know that there's a problem. So in this case, we have a Texas Tech mirror where they thought they properly etched all the photoresist out from underneath the micromirror, but when you actuate it, you actually see some of the photoresist remained, and it causes severe distortions in the mirror as it's actuated. Again, we can quantify radius of curvature, settling and switching time we looked at for this particular mirror, as well as what are the heights of the deformations, and we can even model what that does optically if you're trying to focus with that. And then again, pictures are nice, but a lot of times you're going to also need the quantification. So here, if we're applying a sinusoidal drive signal, I can very easily see the asymmetry in my translation. I only go about 2 microns in one direction, and I go almost 12 microns in the other direction. I can look at translation versus drive voltage and make sure if that's linear or not, and you can see in this case it was not linear over the whole range. And so you can really start looking, are there stiction problems, are there other things going on with the device that need to be handled prior to commercialization. Another very interesting thing is confirming the mechanical models that you use in the development process. So here on the left, someone was looking at a cantilever sensor array, and they knew that it should have resonance frequency around 950 kilohertz. Well, we actually found that the highest resonance frequency was at 953 kilohertz. But the other thing to notice is that while the overall motion shown in the video, the deflections do actually match the model, you can see a big variation across the cantilever arrays. And we ultimately traced that back down to there was different thicknesses of each of the cantilevers that was unexpected from the process. And so some deflected more than others, and that means some would be a more sensitive detector than others. We talked already about using region finding software, so you can take a complex device like you see here, break it into component regions and characterize them separately for lateral dimensions, XY deflections, distortions, and rotation characteristics. So there's a lot that you can do with your device. Once you can measure it easily and rapidly and flexibly, you know, there's a lot you can learn from quantification of the characteristics. Just another example for beam deflectors. So here we were looking at a series, and what we were trying to do was evaluate crosstalk between mirrors. And so we could activate multiple mirrors at once, as you see here. We also did tests doing one mirror at a time to see whether there was electrical or mechanical coupling between one device and the next. And here we characterize sag, bow, deflection, overall range of tilt motion, things like that. And then unfortunately, this is the one video that I know doesn't work in the presentation. I was unable to locate the original one. But this is an interesting thing where you can even use the dynamic characterization to look at thermal responsivity of devices. So this was a joint project between Sandia, MIT, and us, and we wanted to look at an optical switch. And it was very important to understand how it deformed when it was in the off position and essentially a high-powered laser was heating the device up. And so we did a series of experiments where we timed laser heating pulses with our strobing, and were able to characterize the overall peak-to-valley deflection of the device when the laser was on and off. And we looked at that. We looked at a variety of devices with different coatings, as well as under different drive characteristics. And we were even able to figure out the threshold of plastic deformation, so essentially the amount of power this optical switch could handle before it was permanently distorted through changes in the polysilicon structure. So this was a really nice experiment that was done to show kind of more advanced quantification than simply driving a device at a given voltage. We have found the need over the years to support custom analysis and hardware control. So the MEMS field is so varied that there's people that want to use their own heater stages, they want to be able to use their own drive instrumentation, automate various probe planners, or even do analyses that are either proprietary or which are not standard in the software. And so we created actually some interface points where you can write things in MATLAB, you can control external hardware via TCP/IP, and even our system via that. So people have advanced command and control algorithms that they've written that can control our instrument, our analyses, as well as inserting their own. And so this is just something to consider in MEMS devices. You know, comprehensive packages are good, but you know, what is the capability of extending that as new applications or new problems arise? So that's about the end of my talk here today. I just wanted to kind of summarize here that, you know, in our experience, 3D microscopy really provides very comprehensive MEMS characterization. It's a nice combination of fast measurement speed, extremely high accuracy. It's It's non-contact and non-destructive, and it provides both static and dynamic capability. It's hard to talk, especially with the proprietary nature of the various devices, about the applications in great detail, but one can characterize in-plane and out-of-plane motion, do Bode and Nyquist plots. You can look at lateral dimensions, steps, and roughnesses. And then, over the years, there's a lot of customization and optimization for the MEMS community that has to come into the measurement devices. And so that's everything from the specialized objective that we call a through transmissive media objective to look through at encapsulated devices or devices in environmental chambers, all the way to looking at film analysis, having MATLAB and TCP/IP control, and customized fixturing. So, that concludes my talk for today. I'll now open up for questions, and so please hold on the line. So let's see what the overall questions here are. So please, if you have further questions, love to hear from you. So one question here is, what is the maximum frequency that can be measured dynamically on the device? It's about 2.4 megahertz right now can be measured on the devices. So anything from complete static devices all the way up to 2.4 megahertz. Someone asks, can we measure velocity and acceleration of the motion? We can actually measure both of those. So we have advanced capability in our database where we can look at position, and we can also look at derivative of position, so we can give people calculations of both velocity and acceleration. We also have the ability to combine multiple metrics. So say it's important to know, in terms of a pass-fail criteria, some combination of tilt angle plus displacement has to be less than a given value. You can combine results comprehensively to get more in-depth characterization of devices. Someone asks, do you believe that we can look at seal-to-shaft contact behavior? We have, in a variety of situations, looked at contact of devices. Laterally is easy. Vertically, if one is on top of one another, we need some level of transparency of devices. Another area where we've looked at contact behavior is, since we can look through these encapsulation materials, we've actually had people press, for instance, glass or other material against devices, and you can look at the bearing ratio and contact area under various pressure conditions. Yeah, and so some further clarification. Can we strobe with a 6,000 RPM shaft with surface features around 15 microns? We can actually strobe at that level. We'd have to look and make sure that the motion is truly periodic. Another person asks, how do we handle the light level? Because it seems like you need a lot of light if you're strobing, and that's true. We actually use extremely high brightness LEDs and a fairly optimized design in our MEMS metrology system so that we can get maximum light onto the sample. So there have been situations where we've been challenged with light, but for most applications, it's not been an issue. Someone is asking, they ask, can I mention more about the enhanced lateral resolution? And yeah, just very briefly, that technique, it's called Acuity XR in terms of an option on our microscopes. We developed that about 3 years ago, and what it does is it takes a series of measurements of a device of a part, combines those multiple measurements along with a kind of a comprehensive optical model of our system to remove the blurring effects that are introduced by, any optic as it images a device. And with that combination technique, we've actually shown, as I said, more than a 3x improvement in lateral resolution and been able to go to features down to 130 nanometers wide being characterized. I'd say for metrology of features, we probably still can't go much below 200 nanometers, but we can certainly detect down to about 130 nanometers with this advanced measurement technique. All right, so another person asks, what materials can we measure and what reflectivities? Essentially, this system can measure almost any material you can put under it. So we have measured things as rough as paper and the black foam that's used by researchers in laser fusion experimentation, all the way up to mirrors that are coated to be 99.9% reflective. Surface roughnesses we can handle from microns of RA all the way down to angstrom level RA. So we have a broad capability of surfaces that can be measured on this one device. And with that, it looks like we're out of questions for now. If anyone has further questions, I guess. Okay, we got one more, and then we'll wrap it up because we're approaching the hour here. So someone asks, what is the slope range of the microscope? So on smooth surfaces, we can measure essentially from 0 degrees up to about 54 degrees of slope. On rough surfaces, we can actually measure to very nearly 90 degrees. So even with a 20x objective, if we're looking at a metal surface, we've been able to measure to 88.5 degrees with no problem. On a smooth surface, we're limited by the microscope optics, and so that confines us to about 50 degrees, a little higher than that. All right, well, with that, I think we will wrap up the presentation. Again, thank you everyone for your time today. My apologies. Yeah, 90 degrees, one last thing, 90 degrees is based on scattering. So thank you for your time. I am happy to entertain any further questions offline for you. We're happy to talk about, sample measurements and other things. And please take the time to fill out those 5 survey questions at the end of the talk. And again, my apologies for the technical difficulties at the start of the presentation. So thank you all, and I hope to hear from you soon. Bye.
The organizer has ended the session, and this call will be disconnected. Goodbye.